Welcome back to PodMister channel. For beginners setting up an energy storage system, there's often a need to expand storage capacity. Transitioning from using a single battery to multiple batteries raises the question of how to connect the multiple batteries into a battery bank to meet your system's needs. Firstly, there are two ways to connect the batteries into your battery bank: series and parallel connections. In a series connection, the voltage increases while the capacity remains the same. For example, connecting two 100 amp hour 12.8 volt battery in series results in a battery bank with a voltage of 2 times 12.8 volt equal 25.6 volt, while the capacity remains at 100 amp hour. In a parallel connection, the capacity increases while the voltage remains the same. For example, connecting two 100 amp hour 12.8 volt batteries in parallel results in a battery bank with a capacity of 100 amp hour times 2 equal 200 amp hour, while the voltage remains at 12.8 volt. Now considering the most practical and straightforward concerns, will different connection methods affect the total energy capacity of the battery bank? Will they affect the battery bank's endurance? We can use the concept of watt-hour to compare and analyze. Watt-hour represents the amount of energy a battery can deliver over time at a certain power. This can be calculated by multiplying capacity by voltage. Suppose a 12.8 volt 300 amp hour battery bank is fully charged and has 3,840 watt-hour of energy. It can power a 100 watt industrial light for 3,840 watt-hour delivered by 100 watt, which is approximately 38.4 hours. Understanding the relationship between the battery energy and endurance, we can now look back at the previously completed series and parallel battery banks. By multiplying capacity by voltage, we find that both configurations yield 2,560 watt-hour. This shows that the total energy capacity of the battery bank does not change with different connection methods. So what factors should we consider when determining the suitability of series versus parallel configurations for our systems? Firstly, consider the compatibility of your system voltage. The system voltage of your equipment and components is a crucial factor. If your battery charge controller and inverter operate at 12 volt, you must ensure that the battery bank voltage remains at 12 volt. In this case, the parallel connection of multiple 12 volt batteries is the best choice. Smaller systems can use 12 volt, while larger systems should consider 24 volt, 36 volt, or 48 volt. Here's a simple reference. 12 volt systems are typically suitable for systems below 3,000 watts. 24 volt systems for 3,000 watt to 4,000 watt, and the 48 volt system for 5 kW to 12 kW. Larger systems usually choose higher voltages because at the same power level, the higher system voltage results in lower current, allowing for smaller gauge cables and higher system efficiency. Lower current reduces energy losses in cables and equipment, while higher current requires thicker cables to prevent overheating and energy loss. Higher system voltage reduces current, minimizing resistance losses and improving overall system efficiency. In summary, the factors to consider when configuring system voltage include but are not limited to compatibility with upstream and downstream equipment, load compatibility, power demand, transmission and conversion efficiency, equipment and component costs, cable costs, and feature expansion needs. Next, we will demonstrate a practical operation of 3 battery configurations using 4 units of PO 100 amp hour 12.8-volt lithium iron phosphate batteries, each with a nominal voltage of 12.8-volt and a capacity of 100 amp hour, totaling 1,280 watt-hour. The batteries are constructed from ABS material, weighing approximately 10 kg each, featuring a top handle designed for easy handling and storage convenience. They support continuous discharge and charge currents up to 100 ampere. With rapid charging capabilities, enabling full charge in as little as 1 hour. Integrated BMS ensures multiple protective functions for safe and reliable operation, with a maximum cycle life of up to 6,000 cycles, making them ideal for home, commercial, and vehicle energy storage systems. Firstly, we configure a 48-volt battery bank using the PO HBM 6.2K Pro. Here, the 4 PO 100 amp hour 12.8-volt batteries are connected in series, with the positive terminals connected to negative terminals. It's crucial to maintain consistent wire lengths and gauges between batteries. Upon completion, the battery bank voltage measures 5277 volts, suitable for the 48-volt system voltage. After connecting, the inverter starts smoothly. Next, we will configure a 12-volt battery bank using the PO HV 2.5K 12-volt inverter. Here, the 4 PO 100 amp hour 12.8-volt batteries are connected in parallel, connecting positive terminals to the positive terminals and negative terminals to the negative terminals. The final battery's terminals are then connected to the inverter. Post the connection, the battery bank voltage reaches 1317 volts, suitable for the PO HV 2.5K 12-volt system voltage. Finally, we will configure a 24-volt battery bank using the PO Relap 3K 24-volt inverter, employing a series parallel combination. The 4 PO 100 amp hour 12.8-volt batteries are initially paired in series to create 2 groups, each with a voltage of 25.6 volts and a combined capacity of 200 amp hour. These groups are then connected in parallel and connected to the inverter via the busbar, aligning perfectly with the inverter's system voltage. That concludes our introduction and explanation of series and parallel battery configurations. We hope this information helps you in building your energy storage system. If you have any further questions about battery configurations, please feel free to leave a comment. Thank you for watching, and we will see you in the next video.